All right, welcome everyone. So for our first talk today, we have Christy Hazel from Grinnell College, who will tell us about Mackey homological algebra and Bredon cohomology for cyclic groups.
Great. Thank you for the introduction, JD, and for having me, and thank you all for being here. One quick, just logistical note, I have this QR code that has the full copies of my slides. If you want to have them up, they're also on my website, just in case you want to reference something from a previous slide. But yeah, so I am excited to tell you all about this project that has been joint work with Dan Duggar, where we've been doing some Mackey functor homological algebra computations and then kind of using these to do some Bredon cohomology computations. Oh, and okay, there we go. So before I kind of jump into the content, I want to give some context or motivation for kind of why Dan and I started thinking about these homological algebra computations. So we were interested in this ROG graded Bredon cohomology, which in the equivariant world acts as our kind of analog for singular cohomology. So we have some fixed finite group G, and we're looking at G spaces. And when I say analog of singular cohomology, I mean this is some ordinary cohomology theory. So H0 of a point kind of determines the whole theory. And our M here is recording H0 of a point. And this is represented with by some Eilenberg-MacLane spectrum. So we were doing computations with constant integral coefficients and thinking about general finite groups and configuration spaces. And we are actually able to do a lot kind of in generality, which was really nice, but kind of as expected, we occasionally needed to like really get our hands on some algebra computations and really get our hands on the cohomology of a point. And so we kind of set out with this vague goal of trying to get better at doing that. So studying modules over this constant Z gadget and kind of learning how to do homological algebra over this and hopefully be able to do more computations here. So that was our kind of goal where this started a long time ago. I do want to mention, like, people have thought a lot about the cohomology of a point and a lot about kind of how to work over this constant integral Mackey functor or constant Mackey functors in general. So I listed some names here, some work of Lewis, HHR, Ming Kong Zhang's unpublished work is very kind of building kind of the basics of where we started. Recent work of Basu Day. So just to say, lots of people have thought about this, and we some of the stuff we did and some of the stuff I'll say today has certainly appeared in other places in the literature. Some of the stuff is new. We kind of set out to tell as complete of a story as we could, kind of starting with building these algebraic tools. So just to kind of give some context here. So our project, we had a vague goal, and so it kind of meandered in different places. And so I want to have a kind of a focal theorem for today's talk to have a thing to build towards and kind of understand. So I'm throwing up this theorem here. Certainly, I don't expect you to understand what the heck this says yet. I need to kind of introduce this notation and what all these objects are. So I'll just kind of say briefly what this theorem says, and what I'll build towards is we computed this Mackey functor valued cohomology of a point in these kind of two regions for general cyclic groups that are often called the positive cone and the negative cone. And we also have a nice story for the ring structure in these areas. So the plan for today, I want to give some background on Mackey functors, introduce some of the notation and kind of players that appear in our papers for cyclic groups, really focusing on Z modules, then start doing some homological algebra-y stuff and connect this back to Bredon cohomology, which was our kind of ultimate goal to understand. And then we'll revisit this kind of mystery theorem, hopefully somewhat understanding what all the pieces are. And I'll tell you a little bit about this ring structure. Okay. So if you haven't heard this slogan, the kind of usual slogan for Mackey functors is they're supposed to be the equivariant analog of an abelian group. What do I mean by that? One way to think of this is supposed to give the zeroth cohomology of a point. So it's supposed to be my coefficients for my ordinary cohomology theory. Of course, if I'm working with equivariant points, so I'm thinking about G sets, there's different types of points coming from my different types of orbits. And so if I really want all this data of H0 of a point, I really need a bunch of groups, one for each type of point I could have, equivariant point. And then I need all the maps between them. So that's kind of what a Mackey functor is supposed to encode. So kind of setting the stage here, if I'm thinking about these, different points or different G sets, for any finite group G, this always decomposes into orbits. And any orbit X, so any little transitive G set, is going to be isomorphic to G mod the stabilizer. So if I want to understand these finite G sets, really I just need to understand these pieces G mod H for all my different subgroups H. So for today, we're really going to focus on the cyclic group of order n. And so just introducing some notation here, I'm going to use T for my generator of Cn. And then, of course, every subgroup is just another cyclic group. So for each divisor, I have a unique cyclic group, and it's generated by this T to the n over T. So thinking back in our orbits, I'm going to use theta sub d to denote this unique orbit of size d. So if you want, you can think of this as like a necklace with d beads, and my Cn action is just permuting the beads around. There's this, and we'll see a little bit of this today, this annoying thing that comes up in this world where you have to be careful of when you're working with d and n over d. And so I'm using theta d for the orbit of size d. This corresponds to the subgroup, of course, of size n over d. So just something to point out. Okay, so I have these different orbits, one for each divisor. And so I can fit these together in what I'm calling an orbit lattice. So over here, C45 is going to be our favorite group for the next 40 minutes or so. So here is the orbit lattice. And so I am ordering things here where I'm going to have an edge going from theta d to theta d1, if and only if d1 divides d2. This edge is indicating I have an equivariant map between these orbits, and you can like sit here and squint and convince yourself that happens if and only if d1 divides d2. Of course, there's not a unique map, but I'm just kind of recording when there is a map in this little lattice. So here's our kind of rough working definition of a Cn Mackey functor. So I'm going to think of this as a functor from this Cn orbit lattice, or really the opposite lattice, to abelian groups. So every time I have an arrow here in my lattice, I of course get an arrow going the opposite way. I'm going to call those my restriction maps. But then part of being a Mackey functor is that we also get these wrong way maps. So then I get the transfer maps going up. And then one more type of map comes out. So here I've kind of filled in. So at every divisor, every orbit, I have one of these abelian groups. And then I have my purplish blue maps going down as my restrictions, my orange transfers going up. And then I also have this kind of residual action by my Cn. Or really, I have this Cn mod Cn over D action at each spot. Such that a bunch of compatibility stuff that I won't write down for now, but kind of coming from how these are inherited from these maps of orbits. And so we need to kind of have that preserved under our functor. But okay, so a Cn Mackey functor is this diagram of abelian groups, kind of indexed on the divisors of n, and then I have these kind of double maps anytime I have a divides relation. So the main thing we're going to look at today, we're going to look at modules over this thing, is the constant integral Mackey functor. So this is the thing that constantly spits out z at all my orbits. My restriction maps, so my kind of right way maps are all just one, so they're the identity. And then if you kind of trace through this compatibility stuff, it actually forces the transfer maps to be multiplication by, I look at the ratio of my divisors. This is the same if you're used to working with Mackey functors. If you sit down and do the little arithmetic, this is the index of the corresponding subgroups in each other. Oh, and then my action is just the identity as well. So again, our favorite group of the day, C45. Here's the constant Z Mackey functor for C45. Okay, let me introduce another example. So if I have a module over the group ring, so my C adjoins Cn, Z adjoins Cn, module W, I get this thing called a fixed point Mackey functor. And these will come up kind of later in the talk as well. So here, what this does is it eats an orbit theta d and gives the kind of corresponding fixed points where I look at the corresponding subgroup. So my FPW of theta d is the Cn over d fixed points. My restriction maps are my just kind of inclusions. And again, you have to kind of squint to check that things are going the right way, that I have bigger group going to smaller group when I restrict down. And then my transfers are these averaging maps to kind of take a generic point and produce a fixed point by looking at its orbit summed together. Okay, so the kind of quick facts so we can start doing some algebra and homological algebra. This category of G Mackey functors is symmetric monoidal. And so I have something like a tensor called the box product. And then my units, this Burnside Mackey functor, which we don't need to mess with today, but it's there. And then the one just warning, if you haven't done a lot of work in this area, so this box product is defined as some left con extension. And when you kind of trace through the formulas, it's just more complicated than the maybe naive guess you would have. So the naive guess might be, let me just like tensor things level wise. That is not what the box product gives unless you're at the very bottom of this lattice. So if you're at G mod E, it is just the tensor product, but in general, you need to kind of quotient out by these relations coming from the transfers and restrictions to make your kind of compatibility work in the right way. So this is partly what makes doing, in my opinion, doing algebra hard over these Mackey functors. Is the box product is just hard to get your hands on. But with that said, this constant Z Mackey functor is a ring object here. So it's what's often called a green functor. And we do have a nice kind of condition for what it means to be a Z module, so a constant integral module. So this happens if and only if the restriction followed by transfer is always multiplication by the ratio of these divisors. So just writing this for Cn. In general, you want to make sure your multiplication by the index of your subgroups. So this is nice. Again, this kind of comes out by tracing what it happens when you box with Z and kind of writing down all these things. But this is a very concrete thing to check. And for example, this fixed point Mackey functor is a Z module. It's not hard to see if I include my fixed points and then take this little averaging map, that's of course just going to multiply by however many T's I have, which is exactly my D2 over D1. Okay. So we have set the stage with this ring object. This is constant Z Mackey functor. We have some idea of what modules over it look like. So let's start to do some algebra. So the first thing we might want to do is have some ideals. So the first way we might try to make an ideal is take some elements and generate something. So here I'm going to use I sub D for this ideal of my constant Z generated at this theta D spot. So here's our favorite group again. So if I look at C45, here's my constant Z Mackey functor. If I want to build I5, so this is supposed to be the ideal generated at the theta 5 spot. So I want to imagine like dropping a 1 here in this yellow highlighted spot and letting it freely move around my diagram and just pick up everything it can pick up. So when I do that, I get this kind of diagram of subgroups, kind of tracing this through. If I have a 1 here at the yellow spot, I would move down and down again, pick up Z's. Okay, once I'm at the bottom of my diagram, I can transfer up and I'd get a 5Z. I could transfer up again and get, I guess, 15Z. But I also could have started at my yellow, gone down, and then diagonally over to get a 5Z. And so I end up getting this diagram when I trace through. I could also take the quotient and I get this nice little Mackey functor, this module over Z, where I have these Z mod 5s. Great, so this is one more kind of way of building these modules, and these come up when we start, sorry. These come up when we start looking at Bredon cohomology. Oh, and then I put one more little example up here of I9. So looking at something that's not necessarily a prime. So here, if you drop a one, you can kind of trace through what happens again. And you get this kind of layered thing where I have z's down here. I always end up getting z's below everywhere that I drop my one. And then I have a layer with 3z, and then my kind of top layer is 9z. And this is my corresponding quotient module. Okay, so those are my ideals. If I wanted to keep just kind of learning how to do algebra over this, the next thing I might try to create are free modules. And so those are also important for this story. So I'm going to use f theta d for this free z module generated at theta d. And the kind of intuitive idea here, so I guess now we're looking at C9, is I want to, if I'm building f theta 3, imagine like dropping a generator and then kind of letting it freely move around my Mackey functor diagram, only imposing the relations needed to get a z module. So f theta 3, I'm supposed to drop a generator here. Here I'm supposed to have a C9 mod C3 action. So I get 3 copies of Z coming from just twisting that generator. If I want to push that up to the theta 9 spot, I'm supposed to have a C9 action, but I'm also supposed to have some compatibility with this restriction map. And so I don't get any new generators here. This is really just restricting those 3 there. Then I could transfer back over, but okay, I have to be a Z module. So this just has to be times 3. And then so on. So I guess I'll just say if I want to transfer down to the theta 1 spot, now I'm supposed to have a C9 mod C9 action. And so this ends up just folding my generators together and so on. So these are these free modules. Oh, and I had one other little example. I would probably hope that my constant Z is a free thing. And it is one of these types of free things. If I generate at the theta 1 spot, I just get the constant Z. Okay, 2 little facts. So, okay, if these are, I'm calling these free modules and like they're freely generated, but they also should satisfy the kind of usual thing that mapping out of these is very nice. So if I map out of one of these f theta d's, all I need to do is pick something at the theta d spot from my Mackey functor m, send my generator there, and that gives me a unique map. And then I also have this kind of neat fact on here that came in handy. This is kind of a hand-wavy definition of these free modules. It's a nice way to think about them. One way to kind of get your hands on them a little bit more is you can prove that these are isomorphic to this fixed point Mackey functor where I look at the permutation module for theta d. So this is another way to kind of think about these free modules. Okay, so far, just kind of building our algebra toolbox, we've defined these Z modules for cyclic groups. We have some notion of some ideals that are in these, and these are the ideal generated at some orbit. And then we also have some notion of the free module generated at some orbit. Our last kind of just purely algebra play around example, let's try to do some homological algebra. And so let's try to build some free resolution for this quotient module. So here I'm looking at Z mod this ideal, and I'm kind of starting to build this. So okay, of course I'd have a Z surjecting onto here. The kernel is my ideal generated at the spot theta D. So I should probably come and hit that with my f theta D. Okay, you can kind of get your hands on this by thinking about the theta D spot. So here I have D copies of Z, theta D orbit of Z's. And then I'm mapping to my constant Z Mackey functor, so I just have a single Z. Here in pink, I'm calling the generator of this alpha, so it's going over and hitting my 1, which is my generator of Z. If I think about my twist map, so my C in action, T alpha has to go to T times 1, which of course in constant Z, those are just equal. So my kernel in this theta d spot is generated by alpha minus T alpha. And so I can kind of complete my resolution. So my next spot would be to introduce another theta d to come hit that generator of my kernel. I'm calling this 1 minus t because it's going to 1 minus t applied to the generator here. And then the kernel of this map, if I think about the theta d spot, is this take the generator and sum up by all your actions of t. And so then you can come hit that with some sort of diagonal map. Okay, so you can, partly showing this just to say you can really get your hands on these in this kind of concrete way and start building these things. And then you can go do some homological algebra. Okay, I haven't really told you enough to compute these, but I wanted to put this formula up since it will reappear when we start doing cohomology stuff. So you can compute Tor and Ext for these different quotient modules. And the kind of nice little formula that comes out, if I look at Z mod, the ideal generated at the theta D spot, with Z mod, the ideal generated at the theta C spot, I get Z mod, the ideal generated at the GCD. And this is at 0 and 3. This is a computation you can kind of get your hands on, which is nice. The kind of nice little fact is this is the same computation you get for the X one as well. Great. So my next part, let's actually start connecting back to topology. So we've kind of gotten our hands on some algebra. Let's start using that algebra a little bit. So as I said, we were interested in this Bredon cohomology story. So we're really interested in computations over this Eilenberg-MacLane spectrum, so HZ underline computations. Using this kind of machinery built up by Scheda and Shipley, we have the zigzag of Quillen equivalences between HZ underline modules and chain complexes of Z underline modules. And so, okay, if we're interested in doing computations in this homotopy category, we can kind of push them over, if we're careful, into computations in this derived category. And so a lot of our work was saying, let's just work in this derived category and try to do everything here and then transport it back over. So in this, HZ land, kind of one of the most important objects to understand are these representation spheres, or HZ smash these. And so we want to really know what those basic objects are over in the derived category. So here's our example. I'm going to focus on in odd for the rest of this talk. I mean, a lot of this stuff goes over for in even. You just have to think about the sign representation, and it's just even more stuff to keep track of. So I'm just going to focus on in odd for that reason. So if we're thinking about representations for Cn, we have these irreducible representations coming from thinking about C. So these are two-dimensional real representations where I have some primitive nth root of unity, and my lambda of k means I take that, raise it to the k, and my t action is multiplication by that. I'm going to focus in on a divisor, and I'll say eventually why it's okay to do that. If I have a divisor d of n, then I'm going to use this lambda sub d for this lambda of n over d. The kind of appeal of doing this, there's a few, but one is the lambda sub d. The d is really what a generic orbit looks like in this representation. So again, this is one of these places where you want to there's good reasons to maybe choose either indexing. So the n over d is the power I'm raising this primitive root of unity to, but then like a generic little orbit in there will look like a theta d. We'll have d copies. So I'm going to use lambda sub d. So still living kind of in topology land, my S lambda d would be the 1-point compactification of this. So, okay, back to our favorite group of C45. So lambda 3, I would be taking a 45th root of unity, primitive 45th root of unity, raising it to the 9th power, or wait, 15th power. Division is hard. And that would amount to rotating by 2 pi over 3. And so here is my complex plane, and I've drawn these rays coming out from the origin, and these get permuted by my action. So there's a kind of a 3-orbit. So when we 1-point compactify, I get this picture. So I have my origin, and then all my rays meet back up at infinity. And I get this kind of beach ball picture where I have my 3 kind of panels glued in. So this is my geometric picture. And the way I want to get into this derived category is I want to think about the cellular chain complex for this and think about how I would build that. So I put this over here. And really I'm thinking about the reduced cellular chain complex. So down in dimension 0, I have these 2 fixed points that I glue in. So these are F theta, or these are theta 1 orbits. So I'm going to put down an F theta 1. And I'm just putting down 1 because I'm working reduced. In dimension 1, I have these kind of 3 1 cells that are getting rotated. So that's a theta 3 orbit. So I want to put down an F theta 3. And then in dimension 2, I kind of glue in these orange panels. And that's, again, a theta 3 orbit. And then my map here, if I wanted to think of like gluing it, maybe I'll think of this one little orbit. I would glue along kind of the front-facing 1 cell, and then I'd have to glue in the backwards direction for the other one. So this is how you can kind of geometrically think of this 1 minus t. Okay, this little chain complex is what I'm going to think of as now my representation sphere. And okay, there's nothing special about 3 and 45. This is really what we'll think of in general. So if I have a divisor d of n, this will be my s lambda d. And I'm going to kind of abuse notation and just call this chain complex s lambda d from now on. I also have the dual of this s minus lambda d. I kind of just flip over this chain complex and end up with this representing my kind of negative representation sphere. And you can check if you do the derived box product of these, you really just get z back in degree 0. So these are invertible objects in my derived category, kind of as they should be. So just introducing some notation so I can start getting back to cohomology. So I'm going to use this 5-pointed star, which is often used for ROCN, for the ROG grading, but I'm going to label it div here because I'm only going to take this stuff given by these lambda d's where d is a divisor. If I take some alpha in this star div, then I can get a chain complex by taking the corresponding derived box product of all my S lambdas, or the corresponding box products. So for example, S lambda D minus lambda C, I would take the lambda D complex and box it with the S minus lambda C thing and build this up. Okay, now I can have a kind of purely algebraic definition of what it means to take this ROCN, or the divisor portion of the ROCN cohomology of some chain complex. So I'm just taking my internal hom in the derived category, my H alpha, I hom into S alpha, my H lower alpha, I'll hom out of my S alpha. So this is a very algebraic definition, and we can kind of play around with chain complexes to compute these things. Okay, and the key fact here is that if I'm interested in computing the cohomology of a point, so this thing over on the right in my spectra land, my HZ land, this is isomorphic to feeding in just the chain complex that's just Z concentrated in degree 0. So I can try to understand this thing on the left, which is all just kind of algebra questions, to get at the thing on the right. Okay, and then a kind of natural question, if you're used to working in this land, this star div is not all of ROCN. There are some representations not in here. So there's these S lambda of Ks where K is not a divisor. And you really, if you're wanting all of ROCN, you're supposed to take like S lambda of 1 through n minus 1 over 2 or n plus 1 over 2. I always forget. Um, but okay, the nice fact here is after smashing with HZ, I can really think of this lambda parentheses k as one of these lambda subdivisors. And the divisor I take here is the GCD. So we can really focus on this star div without losing information about the cohomology of a point. Great. So now our kind of goal we set out to do was compute this H star div of Z. And I'm just going to kind of drop the Z underline for short. So let's start doing that. So the first thing we might try to do is just think about an integer plus or minus some single lambda. If we trace through the definitions, this just amounts to computing the homology of one of these S lambda B's that we wrote down before. And these complexes just have 3 terms, so that's not too bad. So here are these written again in red in this kind of bluish purple. So my S lambda B is concentrated in degrees 2, 1, and 0. I have my free things, my F theta B to F theta B, and then a constant Z. And then here's my S minus lambda B. At the beginning of our talk, I was playing around with this Z mod IB, and these maps and pieces exactly appeared in this free resolution. And so we're going to kind of exactly get these pieces popping out, which is nice. So this was the very end of that free resolution. And so in degree 0, I get this Z mod IB. And then here I had this kernel that I had to go hit with another F theta B. So if I chop off here, you can check, you get a kind of constant Z. And then my S minus lambda B, here my co-kernel is this IB, this ideal generated at the theta B spot, and then I have zeros elsewhere. So this is the rest of my free resolution. Okay, so we're kind of already using our algebra skills to kind of compute these first tiny pieces of this cohomology of a point, which is nice. Okay, I put this slide up. I'm not going to go through all the pieces, but this is partly to say these Tor computations are kind of the next thing you can use. If you wanted to, oh, sorry, my Zoom thing, of course, is in the way of my hand. If we wanted to compute the next part where we had 2 representations, we could write down this Kunith spectral sequence for thinking, because this is defined to be my S lambda B box my S lambda C. And so I get this kind of spectral sequence where my E2 page is given by these Tors. And if you write down the cohomology, kind of the thing you just need to know is how to do Tor of these Z mod IB with the Z mod IC, which you can compute kind of using these free resolutions, I guess once you learn how to box with these things as well. I'll maybe just mention you get this kind of one possibility for a non-trivial differential. And I have this Z mod IC plus Z mod IB with Z mod their GCD including. And you kind of get the co-kernel that you might expect from working with the same kind of or similar looking sequences in just abelian groups. Here I'm including the GCD, and then I have BC, and so you might guess you get the LCM. Okay, I'm going to now cover this because it's too much to look at. The punchline is that this is doable using these Tor computations, and again, just kind of getting your hands on these things, and it's not too bad. And then you get this kind of next little piece of the cohomology. So if I want to do H lambda B plus lambda C minus some integer, oh, sorry. You get Z mod, this ideal generated at the GCD, Z mod, this ideal generated at the least common multiple, and then a Z, of course, in degree 4. And then zeros elsewhere. So for all my other stars in Z. Okay, the other kind of little punchline that I'll mention is that this pattern of taking GCDs and LCMs starts coming up. So maybe let me go back really quick. If you were to run, if I wanted to take 3 lambdas and write down this Kunith spectral sequence, I end up having to take, these different GCDs of 3 terms with pairwise GCDs, pairwise LCMs, this sort of elementary number theory stuff starts coming out. So this cool sequence of numbers comes out that we were calling this GCD LCM sequence. So let me define this. So our setting is we have k divisors of n, b1 through bk. Once I fix that list of k divisors, I get a sequence of numbers indexed on j. And okay, here's this gross formula, but the orange punchline here, this is the GCD of all j-fold LCMs. Okay, let me make a few remarks to make this look slightly less weird, maybe. So if my j was 1, so my first number in the sequence, then I'm taking the GCD of all one-fold LCMs. So I'm just taking the GCD. So the sequence of numbers starts with the GCD. All the way up at the top, if I plug in k for my j, then I'm taking the GCD of all k-fold LCMs, which means I'm just taking the least common multiple. You can check just kind of by definition that the jth one divides the j plus first. So the kind of idea here is I have this sequence of k numbers corresponding to my k divisors. It starts with the GCD, ends with the LCM, and kind of each number consecutively divides the next one. So kind of building up this list of divisors. And then the last little remark on here, if your numbers are already ordered in this way, that they consecutively divide one another, then I'm just picking out the jth one of these. So I'm not changing them. Okay, so here's that theorem with all the question marks kind of revisited from the beginning. So if I have k divisors, I can look at this portion of the cohomology of a point where I take those lambdas and either subtract an integer or do an integer minus those lambdas. So the first thing is saying if I have my representation here is positive and I'm subtracting an integer, then I get Z mod this ideal where I am looking at the ideal generated at these funny GCD LCM sequence. So when j is 1, so in the 0th degree, I'm just looking at the GCD. At the 2k minus 2 spot, I guess, I'm looking at the least common multiple. And then these are all concentrated in even degrees. And so I'm kind of building up to there. And then I have a constant z in the top degree. Okay, and then there's some similar-ish formula for my negative cone. So where I have an integer minus these lambdas. And here I have a bunch of these ideals in this odd degree. And then at the top portion, I have one of these ideals corresponding to the LCM. But okay, the specifics aren't as important of just you can kind of do this computation and you get this cool GCD LCM sequence popping out. Okay. In my last few minutes, or last 5-7 minutes, let me say a little bit about the ring structure for the positive cone and then the negative cone. So the positive cone, so the portion where my representation is positive and then I'm subtracting or adding an integer. There's kind of 2 special elements I need to tell you about to get this ring structure. So the first is this Euler class. And kind of geometrically, you can think of this as like including the fixed points into my sphere. And if my action on my sphere is non-trivial, this is a not equivariantly null map. In chain complex land, here I'm including my f theta 1 into the degree 0 piece. So that's kind of the chain complex analog of that. This map is just the identity in degree 0. And I'm going to call this map A sub B. And you can, write down chain homotopies and even check that this map really has order B and really generates this class of maps, which is nice. And so this generates my h lambda b, which is, this is in degree lambda b minus 0. So this is just a z mod ib. So I have these Euler classes in h lambda b for each divisor b. Also for each divisor, I have these orientation classes. So here, this is like supposed to pick off my top cell. It's kind of one way to think of this. So I have a z now in degree 2 mapping in. And you can check, I mean, if we go back to our computation, this is supposed to be a constant z, and you can check that this map has order, additive order infinite, and generates this group of maps. So, okay, I get this Euler class, and then I get this orientation class. And let me put both these parts up. So the kind of theorem is that this positive cone regen is generated by this Euler class and this orientation class subject to the torsion relation on the A's, and then this kind of generalized gold relation. So this gold relation, it appears in HHR for thinking about n being a prime power, and then in work of Basu-Day, and then also in work of me and Dan, you can generalize this to any n where b and c are divisors. And okay, what this gold relation is telling me how to do is if I take an a and a u, where a corresponds to b and u corresponds to c, I have a relation with ac and ub, and the kind of factors, the integers that come out are these b over the GCD and then c over the GCD. Yeah. Of course, if you're in the case where b and c are just powers of the same prime, one of these sides will just be 1, and one of these sides will be the p to the prime to the difference of the exponents. So kind of recovering the gold relation from HHR. Okay, so this is kind of a nice story. I have these Euler classes, I have these orientation classes, and that kind of gives me all of my positive cone. I'll just say a little bit about this negative cone region. So here's the part where I have an integer. That's what my, I guess, 6-pointed star here is. And then I'm subtracting some representation. So this figure, this is from our paper. This is a slice where I'm just looking at one lambda b and seeing what happens. And you'll notice there's kind of two pieces of this picture. There's this edge with boxes. These are supposed to denote z's. Oh, and I guess I should say here, I'm just looking at the theta 1 spot of my Mackey functors. My dots are z mod b's, and then I have this Euler class AB multiplication indicated with diagonal lines, and then my orientation class multiplications are these vertical lines. Okay, in general, there's these two parts. There's this integral edge, and then there's this, what we call the torsion cone. So this integral edge, these classes we can kind of name with some integer over some orientation classes. These orientation classes aren't actually invertible, but the idea is if I multiply by this denominator, I'll land back in H0 and get this multiple of 1. And so I have these classes. And then I'll just quickly say a little bit about this. I know there's too much to really fully grasp this, but the kind of idea is there is a nice story here if you're willing to deal with all the notation. This green cone part, there's this tip of the cone that we labeled gamma sub b. This lives in degree 3 minus 2 lambda b. And we have these tips for every divisor b. And then the way you kind of get the rest of your picture, you take this generator and then kind of propagate down, is this is infinitely divisible by certain orientation classes and certain Euler classes. We just have to be a little careful about which ones. So the orientation classes that divide this are the u sub d's where d divides my b. And then the Euler classes that divide this are my a sub d where b divides d. And so we have this notion of kind of valid fractions that generate this negative cone. The one last thing I'll write is there's actually one other type of a tip of a negative cone that we need. which comes from pairs of divisors. So these two tips, along with their divisibility relations, give rise to a name for every element in the negative cone, and those names are extremely suggestive of what the multiplication looks like. So it's kind of a nice little story. Okay, I'll stop there. I'll say this, is a very tiny bite size of these two papers that we put out on the archive a couple months ago now. I don't know, time is meaningless. But anyway, those papers are on the archive if you're curious to learn more. Thank you.